I will take the next couple of minutes to tell you something about my research or the group's research and what we're going to focus on in the future. And I'll introduce some challenges in renewable energy systems and give you my mostly probabilistic perspective on this. Now, on this slide, you already see the European energy network, or in this case, it's actually the electricity network. And in this talk, whenever I will talk about energy, I will only talk about electricity, although we don't actually have an electricity-only energy system at the moment. But what you can also see on this graph is that the energy system is highly connected and very complex, and it's an interesting system to look at. Now, this energy system is facing some changes. And in the future, we want to have an energy system that looks a bit different than the energy system that we currently have. This is mostly due to society's wish and political aims that are related to climate change issues. So we want to prevent climate change and therefore hopefully contribute with the energy system by introducing more renewable energy sources. So what does that mean for the system? Now, in the past, we've generated our energy mostly with a few large power plants that were distributed where the demand is mostly. And these large power plants then distributed the energy top to bottom to the consumers, which were either households or are either households or industrial facilities. Now, this is changing a bit when we introduce renewable energy sources, because renewable energy sources are distributed not necessarily where the demand is, but where they are most effective in producing energy. So wind turbines are located somewhere offshore or at least close to the coastal borders, for example. Now, another thing about renewable energy sources is that some of them we can actually have in our household or on our rooftops. So using PV panels on rooftops changes the energy system significantly in the fact that we now not only have this from these large energy producers, we carry energy to the consumers, but the consumer is actually also producing energy and feeding that back into the system. So from this top to bottom distribution, we now enter bidirectional distribution, which makes the households or industrial facilities also active participants in the system. Now, for both, even in relevant for both the system of the past and the system we want to have in the future, is climate change. Climate change results in some ways in more extreme weather events in both systems. So the system of the past and the system of the future would struggle or will struggle with that. So as you have maybe heard in the past couple of weeks, there were major outages in Texas due to frozen pipelines and stuff like that. And the cause was extreme weather that wasn't predicted, and then some system failures. And both system components, so the renewable and the past components, were actually failing. So climate change, although we're not focusing mainly on that, but these extreme weather events due to climate change, they are interesting for the energy system or difficult to handle for the energy system. Now, what are the other challenges despite rare weather events and how to handle them? When we look at this gray blob and think it's the demand of an energy system, then what we used to do in the past is that we would follow this demand with the supply. So adjust these big power plants to generate energy whenever it was needed. Now, as we know, we can try to tell the wind turbine or the wind speed to go a bit higher, but we're not very successful at that yet. So with more or only renewable energy, we can't follow the demand anymore. We have to take the supply as it is and handle it. So with this in mind, there might actually be times, or there are very often times, where the supply that we have from the renewable energy sources doesn't match what we want to use at a specific moment in time. Now the big challenge is knowing when that happens, so when are demand and supply not matching, and we can find more. We can figure this out by looking at the demand and looking at the supply, for example, through forecasts, and trying to predict whenever they won't match. So we can think of this as like looking into the demand a bit closer and actually finding out what processes or what is generating this demand. If we're lucky, we might also find ways to shift the demand in such a way that it better fits to what we have as a renewable supply. So the main aim of my group is to understand these future renewable energy systems better and find ways to analyze them with machine learning, but also to help contribute to making them as sustainable as possible. I'm especially interested in the uncertain aspects of these systems. And I'm also looking at these systems from different perspectives. So perspectives in this case, for me, means from the demand side, the supply side, but also the interaction in the system. So human interaction with the system or other component interaction with the system. And the remainder of the talk, I will shortly look into each of these three perspectives, and I will take most of the time with the demand side and then have some shorter parts on the supply side and the interaction. Okay, so let's start with the demand side. Let's assume we want to forecast the electricity demand to find out a bit more. And this is on the top, you see the electricity demand of the UK over the past, roughly 10 years. And it's the electricity demand as measured on the transmission grid. So there you can see rather steep decline in energy usage. That is partly due to the fact that the solar or the PV panels on the distribution grid are not measured by this. So all the UK has not gotten really, really good at energy usage and reduce its energy that much, but some of the energy is now produced locally on the distribution grid and also used on the distribution grid and is therefore not measured on the transmission grid where the large power plants are. Now, what's special about electricity demand is that there's several patterns in there. One very prominent pattern is a daily pattern, which you see the bottom graph. These daily patterns are mainly due to how we as humans use energy and when we get up and, for example, go to work. And they differ according to what kind of day we have. So is it a normal weekday where most people go to work? Is it a weekend? Is it a special day, such as a public holiday or anything in that order? Or is it a proximity day, which is something that we've introduced to account for all the days that are not officially special days, but are very close to a special day? So for example, the time period between Christmas and New Year's, it's not all public holidays officially, but the demand is very different over that period of time. And as you can see, it's a very regular pattern with like the weekdays or the days where people go to work and their industrial facilities are running is higher than on those days where these facilities aren't running. Now, apart from these calendar-based variables that determine how the demand looks like, we also have a large influence of the weather. Now, I want to introduce you to two derived weather variables that tell or that are highly correlated with how the demand is, how much demand we have. So on the one hand side, we have the effective temperature. So effective temperature is a measure that smoothly averages over the past temperature. kind of accounting for the fact that just because it's getting hotter this day doesn't mean that we automatically quickly turn off the heating or something like that, but it usually takes a bit of time till we adjust our behavior. So we have a smooth average over the spot temperature TS, that is, and then that is usually the past 4 hours or past 4 days, depending on the horizon, and then sort of accounting for the fact that some things like our buildings, they heat up, but it takes a bit of time, and so the adjustment to the temperature that we have outside is a bit smoother than just On the other hand, we have the cooling power of the wind, which kind of accounts for the wind chill or the apparent temperature, so how we feel what the temperature is like. And National Grid, so the system operator in the UK, has found out that wind speed has an effect as soon as the when the temperature is below 18.3 degrees, and as soon as it's above 18.3 degrees, this variable doesn't really play a role. Now, when we want to look at the weather in electricity demand, there's lots of ways we can do that. Now, what we've done is that we took a look at the weather stations across the UK that also the national system operator National Grid uses, and weighted these according to the demand that is at these places. So we took the 7 largest cities sort of the UK, and we measured the weather at these points. Or we took into account the weather at these points. We didn't measure the weather ourselves, but used numerical weather prediction models. There are physical models of the atmosphere that describe how the weather is most likely going to be in the next couple, or can describe how the weather is most likely going to be in the next couple of days. What you see here is a so-called ensemble of these numerical weather prediction models. It's these physical models are really large, and but they have some uncertainties, such as what is the initial state of the atmosphere at a specific point on Earth. And as we can't measure everything all the time, what is usually done by the by these weather agencies is that we change the initial condition parameters a bit, and then see how this is going to change over the next couple of days. So in this example, for the temperature, which is measured in Kelvin, you can see that at the start point, all these ensembles, so all these scenarios of how the weather is going to be like, are close together, and then over the next couple of days, they diverge. Now, if they're good forecasters, or if these weather ensembles capture the uncertainty that is the true uncertainty that is there, then they are calibrated. But more often than not, they're actually not calibrated. They're either under-dispersed or over-dispersed. Most of the time, they're under-dispersed, so the true value most often falls in the tails or out of what these ensembles capture. Now, if we want to include this weather uncertainty, then we do kind of want to use a calibrated weather uncertainty, and not an under-dispersed or over-dispersed one. So therefore, we post-process what these weather ensembles are like, and calibrate them to the past, so that they give us a good estimate of the weather uncertainty. How do we do that? We do that by estimating distributions. So we take the ensembles, which are here XM, and then estimate the mean and the standard deviation of these ensembles, fitting them to different distributions. We use different distributions for each of the variables, so temperature is based on a normal distribution, and wind speed, for example, a truncated normal. And on the graphs on the right-hand side then show you that the relative frequency of these temperature ensembles that we've seen in the slide before calibration and then after calibration. They would be perfectly calibrated if they'd be uniformly distributed under that red line. So it works, yeah, it doesn't work perfectly, but they're better calibrated than before. Now, one difficulty or one trouble with that post-processing using different distributions for each of the weather variables is that we lose some of the information that was initially in the raw ensembles. So the raw ensembles capture the dependencies of these variables, so of cloud cover and wind speed and temperature over different time steps. Now, when we fit a distribution to these different weather variables, we kind of lose that connection. And what we want to do now is put that connection, put that back in by sampling smartly from the distributions that we have. So let's assume we have these six ensembles, and at a time step t1 for 3 weather variables v, y, and z. And we order the ensembles that we have. We're usually using the ECMWF data, so the European Center for Medium Range Weather Forecast provides ensemble data with 51 ensemble members. So we order all these ensemble members, or in this case, we have these 6, and we order their values. And so in this case, the V, if we look at if we look at the ensemble member 2, we see that this value for V is the second smallest value that we have in the ensembles. And it corresponds, so that same ensemble member corresponds to being the 5th value looking at weather variable Y, and then again the 2nd value looking at weather variable Z. And we can do that now across these weather variables and across time. Now, when we have sorted these ensemble members, we then can look at the distributions that we fitted before and sample from the bins corresponding to the rank that the ensemble member has. So, for example, at time step 1, we can now, if we want to have these 3 weather variables in our forecast, we can sample from the 2nd bin of the 1st weather variable, the 5th bin of the 2nd weather variable, and then again the 2nd bin of the 3rd weather variable to get our input for the forecast that we then use them for, in our case, the demand forecast. And we can also do that for all the other time steps that we have forecast for. Therefore, retain the dependency structures that were in the raw ensembles that we lost because we fit distributions. And now we put them back in by sampling from the distributions dependent on what the structure of the raw ensembles looked like. Now, if we do this, then we get calibrated forecasting results, or forecasting results based on calibrated weather input. And we can see that for the CRPS skill, so CRPS is a score that measures the calibration and sharpness of the probabilistic forecast. And we can see that post-processing these ensembles, so recalibrating them and making sure that the dependency structures that were previously in there are still in there, actually helps us a bit over using the raw ensembles. So here up is better. It doesn't as much help as with the point forecast. So for example, the mean average percentage error is actually a bit worse, but yeah, if we do the probabilistic forecast, then we should account for these dependency structures. The bottom line is just using no weather information at all, which is luckily the worst you can do. And the plaque is using actual weather data, which also performs a bit worse in the CRPS because it's not a probabilistic estimate. Now, we've calibrated the weather, but we do a probabilistic forecast. So you might argue that we could also calibrate the remaining demand forecast. And we took a look at what current deep learning methods can do, and if they are calibrated, or if it helps them as well if they get recalibrated after the forecast. Now, on the left side, you can see a one-step ahead forecast. And in the upper panel here, it's the one-step ahead forecast for with the uncalibrated results of these methods. And then on the bottom left side, you see the same methods after calibration. So all of them are better calibrated and benefit from a calibration. Now, on the right-hand side, you see the same methods on a 1 day ahead, so 24 hours ahead forecast. And there you can see that they're actually already way better calibrated than, or some of them are already way better calibrated than for the one-step ahead forecast. And when we recalibrate them, then some are actually looking worse, but others benefit. So we're not quite sure yet when recalibration, the demand in the end of the forecast helps us and when it doesn't. And it seems to depend a lot on the method and the forecast horizon. So the next step that we're currently looking at is, do we actually need to post-process both steps, so the weather and the demand in the end, and which method is helping us do that, and when do we need to can we find information in the data when to recalibrate and when not to recalibrate this output. Okay, so far I've been talking about the demand side. Now the supply side isn't actually much different to that, but it has one important difference, and that is sort of that the demand side is a bit dependent on the weather. The supply side is a lot more dependent on the weather, because if you look at wind energy, the output of wind energy is mostly just explained by wind speeds. So this is now ongoing work. We're looking at wind power plants in Germany. So on the left-hand side, you can see a map of all the wind power plants we currently have in Germany. Some are offshore, most are onshore. And as you can see on the right-hand side, this is the total wind generation across all these wind turbines. And we can again see that there are some seasonal patterns in here, but they're not as prominent or not as strong as they are with the demand. So the wind isn't, unfortunately for us, not dependent on the weekend and the weekday, but on what wind speeds are looking like. And it is dependent on seasons. And there also luckily corresponds with the seasons, the demand seasons. So sort of the demand is higher in the winter, and wind speeds, at least in Germany, are also higher in the winter. So that at least is helpful for an only renewable energy system. Now, we're currently simulating this wind power across Germany, because the information for all these wind power plants isn't completely available. And we're using a tool that is called Renewables Ninja, and that I wanted to introduce you to. If you ever wanted to know what kind of solar PV you can put on your household rooftop, then you can have a look at their API and sort of calculate what could be the production of solar on your house. And they also, what we're using that the Renewables Ninja API for is for simulating the wind power dependent on specific wind turbines. Now, what's mostly interesting now with this wind power is sort of integrating not only the temporal dependencies that we've already integrated with the demand, but also integrating the spatial dependencies. There are large weather events, mostly that over a couple of days sort of move across Europe from, most often I think, west to east, and capturing these weather events properly and the spatial relationship between the different wind turbines should result in, or we hope that that results in, better forecasts for the individual power wind turbines, but also for the total power production. Now, this is just what we're currently working on, trying to use graph neural networks to account for these dependencies. And I'd be really happy to talk about this a bit more with people who've done maybe graph neural networks before. We're just starting with that and only in the data collection phase. Now, the last thing that I want to talk about is interaction with the energy system or in the energy system. Now, if we think back about on that graph from the beginning, we had this demand and supply, and what do we do when it doesn't match? Because we have to do something. And the idea is that we can actually interact with this system, and we can use what we have on the demand side and the power we have on the demand side and change our behavior. Now, the idea behind that is called demand side flexibility. So we assume that there is some flexibility that we have to adapt to the energy behavior, either by changing when the energy is used, so having some time flexibility, or how the energy is used, which we then call operational flexibility. And there are some parts on our everyday energy usage that you can probably think of they're really easy to shift around. So it's mostly, or the prime example for households is usually a washing machine. Most people don't really care when the washing machine is running, as long as it is done by a certain point in time. So there's some time flexibility where we could shift this operation of the washing machine. Now, there are also some processes that we think are probably not very flexible. If we think about usage of coffee machines, for example, then no one would really want to wait until the wind is a bit stronger to have his coffee. So there are parts of the system where this time flexibility and operational flexibility is there, and parts where it isn't. Now, the questions that we were asking ourselves is, looking at this flexibility, well, how much do we actually need? If we want to, for example, reduce the peak power demand, how much would we actually need to shift things around to make a difference? And we took a look with something that we term flexibilization project scheduling problem. So given we have a schedule on how our things are running, we introduced some flexibility limits, J and T, to find new start times. So J and T, are used to account for both this flexibility flexibility on time scale and on the operational scale. So J sort of tells us, is there to tell us how many of these processes do we actually need to change to make a difference? And T is used to, well, by how much do we need to change the start times? So we want to find, so given a schedule, we want to find, and these flexibility limits that we predefined, we want to find a new start time such that 1 and 2 hold. How does that look like in the end? Well, what we can see here is the relative peak demand. And on the x-axis, we have J, so the number of jobs that we touched or let the scheduler decide to move around. And theta, which is kind of the amount of time that these jobs were allowed to be moved around, independence of T. Now, what we can see here is that we don't actually need to change a lot to already make a difference in the system. So more specifically, if we take a look at the first column, sort of where theta is 0.5%, then we can see that changing 0.5%, which in this case, I think was roughly 15 minutes. So changing a job by 15 minutes and only changing 3 of a total of roughly 200 jobs already reduces the relative peak demand by up to 15% and up at least 5%. So to change how we don't actually have to change much to adjust the behavior in such a way that it probably fits this renewable power supply a bit better. Now, we've done this with a simple or a basic optimization and not using machine learning. Now, the interesting question was, can agents in a system actually learn to behave like that and to change how they operate their processes such that it better fits the goal that we have, either reducing peak demand or just stay under a renewable energy production curve? And so we introduced an agent system using simple Q-learning for a start, where there are 4 ways in which agent and supplier can interact on the system. So in the first case, which we've called offers, the demand agent can offer a specific pattern to the supplier. So you can say, okay, this is my process X, and it usually runs with power profile PT. And I could change that to a power profile looking like P star T, but it would cost me something. And on the other hand, the supplier can advise the agents and say, hey, it would be absolutely terrible if you use a lot of energy during time steps. In our case, we picked the 6 worst time steps to use energy. And then we have a strategy where both is possible. So the demand agents can offer something and the supply can advise them. And the baseline is that none of these strategies are implemented, and the demand agents just do whatever they were doing before. So in this simple setting, what we can see is that the black line on the top is just when nothing is done in the system. So everything is, all the agents use their energy as usual. The purple line is when the supplier can advise the demand agents to, he basically just tells when the 6 worst possible times would be. And in the last 2 curves that are almost identical is where the demand agents can offer what they could change, and the advice is given. And what we can see is that in a very simple setting, the signaling and rewards for good offers can actually reduce the need for conventional energy by roughly 40% or a bit more, depending on the time of day. So if we take these flexibility, so we've realized that we don't actually need a lot of flexibility, so we don't need to change a lot. So the agents don't need to optimize a lot to make a difference, and we can actually incentivize them in such a way that they don't use energy when it's when the solar power isn't available or something like that. So I'm a bit quicker than expected. So I'm under the aim of what I'm doing, what we're doing in the group is understanding future renewable energy systems, especially regarding uncertainty. And we mostly use these three different perspectives: the demand side, the supply side, and the interaction. And the next step, sort of on the demand side, we're currently working on non-parametric post-processing and doing that if it works in one step. So post-processing of the weather and post-processing of the demand to get a calibrated probabilistic forecast of the demand. And then on the supply side, we kind of want to take a look at how the spatial temporal interactions, how we can introduce them to the probabilistic forecasting and sort of make use of what's already available from the spatial weather information. And lastly, in this system that I just introduced with the agents, there's currently no uncertainty involved, but what we are working on is to include uncertainty, and so have the agents give the agents an uncertain estimate of how the future power supply is going to be like, and then maybe also introduce some notions of risk aversion across the agents. Thank you for your attention, and looking forward to your questions.